Hello APC Mechanics students, today we will solve the past paper FRQ 2004, exercise 1. A rope of length capital L is attached to a support at point C. A person of mass M1 sits on a ledge at position A holding the other end of the rope so that it is horizontal and taut as shown above. The person then drops off the ledge and swings down on the rope toward position B on a lower edge where an object of mass M2 is at rest. At position B, the person grabs hold of the object and simultaneously lets go of the rope. The person and object then land together in the lake at point D, which is a vertical distance L below position B. A resistance and the mass of the rope are negligible. The moment a resistance, we're talking about frictional forces, are negligible, which means we can use the conservation of energy at any point along the motion. Derive expressions for each of the following in terms of M1, M2, L, and G. Then this is important. Now an expression that we obtain should be expressed in terms of these. Now let's start with part A. They're telling us to derive the expression of the speed of the person just before the collision with the object. Now the person here, they're saying that the person drops off the ledge. So the person here is released from rest. Then he will reach the point B. We're interested in determining the speed at the point B, and this can be determined using conservation of energy just before the collision with the object. Then we can say, first let me specify the PE level, then let me take the horizontal level passing through B to be the PE level. So let me state, take the PE level, to be the horizontal plane or the horizontal level passing through B. Now we're gonna derive the expression because they told us so, and it is because a free response problem, but we know that the speed before impact would be given by radical to GH because it's released from rest, and the height H would be just the length of the rope, which is basically L. Then we expect the speed before impact would be given by radical to GL. So now we will say apply the conservation of energy. So we're gonna say that the energy at the point A equals to the energy at the point B. So the energy at the point A is equal to the energy at the point B. Now the energy at A, we have kinetic energy and gravitational potential energy, which is equal to kinetic energy at B plus gravitational potential energy at B. Now that would be the P level, which is 0 and initially dropped from rest, or the person releases himself at rest without initial speed. Then here we can say that the person of mass M1 G, now the height, which is given by this height, and I'm considering that this is the PE level. So this height would be exactly equal to this height, which is the length L of the rope, equal to half M1 V1 square. Now M1 would cancel, and if we solve for V1, then V1 would be given by radical of 2G multiplied by L. That would be the speed of the person just before hitting the rock. Sorry, the object. Now they're asking in part B the tension in the rope just before the collision with the object, and the tension can be determined by applying Newton's second law. So let me say apply Newton's second law. And we know that the Newton's second law is given by F naught equals ma. Now here we're applying Newton's second law to the person, so that would be m1. Now what are the forces acting on the person when he's just before colliding with the object m2? So that's the person. Now for sure we would have the pull of gravity, which is down, and we would have the tension force, which is up along the rope. No other forces, because we're supposing that the person is not in contact with this level surface and neither with the object. So I would say the pull of gravity Fg plus the tension force equals to m1a. Now we know that this is a vectorial equation. It gives the birth to two linear equations, but we're only considering, so the tension at this particular location, it's along the center direction. So let me say projection along the center. Now, what would be the positive direction? In this case, we know that the forces pointing along the center would be in the positive direction. We have the tension to be up, so the tension is positive, and the gravitational force to be negative. Then we can say that that would be minus m1g plus ft equals to m1 multiplied by a. And here let me clarify something. The expression of v1 that we have obtained in part A, this is acceptable because it's being expressed in terms of lng. Now here in this case we're searching for the tension. Now if you isolate the tension, we take this to the other side, then the tension would be given by m1 multiplied by a plus m1 multiplied by g, and the acceleration at that point is given by the centripetal acceleration, which is given by v square over r. Why it is the centripetal acceleration? Because we have projected along the centers, then that should carry the subscript c, the subscript c, and we know that the centripetal acceleration is given by v square over r. What does here v represent? It's v at this specific instant, which is given by v1 that we have determined in part A, and r would be the radius of the circle governed by the person, which is the length L of the string. Then the tension force in this case would be given by m1 multiplied by v1 squared divided by capital L plus m1g, and we know that v1 is given by radical to lg, so m1 radical to gl to the power 2 divided by capital L plus m1g. So this power 2 cancels with the radical, L cancels with L, then we're left with 2 m1g plus m1g, and that would give us 3 m1g. So the tension along the string at which the person at the point B just before colliding with this object is given by 3 m1 multiplied by g. Now in part C we need to determine the speed of the person and the object just after collision. So we're comparing a quantity just after the collision, and this is governed by a phase under which the conservation of linear momentum is dictated. So let me say apply the conservation apply conservation, it's better. And we're gonna say P initial would be equal to P final. Now initially what momentum do we have? We have momentum only due to the person, which is given by m1 v1 plus 0 because the object is at rest. Now they stick together, so they form one object, so that would be m1 plus m2 multiplied by the speed v that we're interested in determining. Then here also let me make the following interpretation. The tension that we have obtained is given by m1 multiplied by g, which is in terms of this constant. For this reason I have replaced the centripetal acceleration by this quantity. Now v would be given by a fractional mass m1 divided by the total mass multiplied by V1, and we know that at this stage V1 is given by radical 2GL. So then the speed of the system consisting of the person and the object after collision is given by m1 divided by m1 plus m2 multiplied by radical 2GL. Now in part D we need to determine the ratio of the kinetic energy of the person object system before the collision. So we need to determine a ratio. So what do we have in the numerator before the collision? So kinetic energy before the collision divided by the kinetic energy after the collision. What is the kinetic energy before the collision? We know that the kinetic energy always has the quadratic term, which is half mv squared. Before the collision, the only object is in motion is the person, which is given by half m1 v1 square, and after the collision we have a combined mass given by m1 plus m2 multiplied by the new speed, which is given by v. Now half with half would cancel. Now here we have m1, v1 is given by radical 2gl to the power of 2, and here we have m1 plus m2 multiplied by v square. V is given by m1 divided by m1 plus m2 square multiplied by radical 2gl to the power of 2. Now this with that would cancel, and we would have m1 divided by, now this power 2 is for both m1 and the denominator, so we can do it like this. Now this with that would cancel, this with that would cancel, and this goes at the top. Let me do it carefully. We would have m1 plus m2 multiplied by m1 square divided by m1 plus m2 square. Now this with that would cancel, and this with that would cancel. The denominator in the lower part would be in the numerator. Then in this case the ratio of the kinetic energy before to after collision is given by m1 plus m2 divided by m1. Now in part E we need to find the total horizontal. Again, before I move to part E, so notice that the expression is given in terms of m1 and m2, and these are accepted since they stated here in terms of the following quantities. Now in part E, the total horizontal displacement x of the person from position A until the person and the object land in the water at point D. Now we know that after the person and the object becomes one object, the motion from this point to this point at the point D is a projectile motion, and it's governed by uniform varied motion under the influence of gravity, so the acceleration is g. Now here we want to determine x. From this point to this point, we know that this is basically L. So it's only sufficient to determine this distance. Then we can add it to L and we would figure out what is x. Now let me assume that the origin is to be here and the positive y direction is up. And we're interested in determining the distance small d, which is this one. So in this case, I'm gonna use the uniform motion along the horizontal, and it's given by x is x0 plus v0 cosine theta t. I'm gonna name this to be the small distance d. We have chosen x0 to be the origin, and here this is a very important remark. Upon collision of the person with the object, the initial velocity at this point is completely horizontal, which means that the angle with the horizontal, which is theta, that would be 0, which means that cosine theta would be 1 and sine theta would be 0. So here in this case that would be 1, and v0 would be the speed v, which we have determined in part C to be the combined speed of the system. So that would be v multiplied by d. Let me do it the following way. So d in this case would be v multiplied by t, and v we have determined to be a fractional mass multiplied by a radical 2gl. And now the only thing left to determine is what does t represent. T can be determined from the vertical motion. Now again, along the vertical we have the following time equation, which is given by y is y0 plus v0 sine theta t minus half gt square. Now we're choosing the initial position to be the origin. That would be 0 as we have justified previously. Why? So if the positive direction is up and this has to be negative because the positive direction is up, then the vertical position at the point D would be negative L, which means that negative L equals to minus half GT square. Now minus cancels with minus. And if we solve for t, if we isolate t, then t is given by the radical of 2L divided by g. Now we're gonna replace this t and the distance t, but that would not be our final answer because we need to add the horizontal distance L. So d in this case is given by v, which is the fractional mass m1 divided by m1 plus m2 multiplied by t, which is the radical, sorry, here we have radical 2gl, multiplied by t, which is the radical of 2L divided by g. Now g with g cancels. Radical 2 with radical 2 would give us 2. And radical L with radical L would give us L. So that would be 2m1L divided by m1 plus m2. So the capital distance d, or we are interested in determining what is, I think, x. So x would be L plus the small distance d that we have determined. Now we can factor out L. That would be 1 plus 2m1 divided by m1 plus m2. Now here we can do the common denominator. And m1 plus 2m1 would give us 3m1 plus m2 divided by m1 plus m2. And this is an accepted answer because it's being expressed in terms of 1m2 and capital M. So in this case, the horizontal distance traveled by the person object system is given by fractional mass 3m1 plus m2 divided by m1 plus m2 multiplied by capital L. Then that's it for me in this video, guys. See you soon in a new one.